Hi, this is Year 2 Pure Chapter 2, Lesson 2, and this is all about functions and mappings. So, first off, we need to understand what a mapping diagram is. And then following that, we're going to understand what a function is, what isn't a function, and what is a domain, and what is a range. So, a mapping diagram we're going to start off with this, which is going to be 2x plus 1. I'm going to plug some values in. I'm going to plug some values, well, based on those plugging values in, we're going to get some values coming out. So when I plug in 1, 2, and say -3, when I plug these in, I know that I get 1 times 2 plus 1 is 3. 2 times 2 plus 1 is 5, and -3 times 2 is -6 plus 1 is -5. Essentially what we've got is a series of ins matching to a series of outs. And for every value that goes in, we have exactly one value that comes out. Now that is clearly implied by the graph as well. There, 2x plus 1, that graph there. Every value I plug in, I know exactly what I'm going to get out. And also, based on every output, I know exactly what went in. So, there are a couple of tests that it needs to be able to pass in order to be able to be a function. For one, it needs to be that based on whatever you plug in, you need to know exactly what you get out. And it needs to be happy enough so that whatever you plug in, it will give you a value out. So if there's a break or an asymptote in the function, or if the function isn't defined for certain values, so for example, if we're square rooting, you can't square root a negative, that won't be a function. It has to be that it works for every input value. Based on any input value you could think of, a million, a billion. You could plug it in and you could get a known output. So, in this case, this is called a one-to-one function. One value goes in and exactly one value comes out. There's one way to make one value, and this is a function. So let's take a look at something a bit different. This time we've got x squared. Now, in this case, we're going to try out 3, -3, -2, and 2, and 0. And when we square those things, we get, well, 3 squared is 9, but also -3 squared is 9. -2 squared is 4. But also 2 squared is 4. So they both map to the same value. And 0 squared is 0. Okay, well that bit there is slightly different from the other bits. And again, we could have a little look at what the graph would look like for x squared. Now, let's double check whether it passes all the tests that we expect. Could I plug absolutely any value in as x? Does it matter whether it's positive or negative? Is there something in there that's going to cause an asymptote? Well, no. It could be any value that I can plug in there. Okay, so we think it could be a function, so let's check again. Let's see if there's anything else we need to know about. So I can plug any value in, and based on plugging any value in, do I know exactly what I'll get coming out? Well, yeah, I do. Okay, and so that passes the threshold for me to consider it to be a function. Now all we need to do is define which type of function it is. Now this is called a many-to-one function. The reason it's called a many-to-one function is because there's many different ways, for example there's that way and that way, to produce one value. But remember, you can plug whatever you want in, and based on whatever you plug in, you know exactly what you're getting out. And so that's a function. So let's take a look at something that's a bit more problematic. Now in this case, we're going to take a look at root x. So we're going to start off with 9, 4, and 0. Now 9, the square root of 9 is 3, but also -3. And the square root of 4 is 2, but also -2. And the square root of 0 is 0. And so what's happening here is, if I plug 9 into the square root of x, if I square root 9, I don't know what I'm getting out. I have no idea. Just don't know what I'm getting out. Now typically what will happen if you put say y equals root x into, say, GeoGebra, you'll see something that comes out like that. Okay, so 9 going in gives us 3 coming out. But what's happened is GeoGebra has applied a restriction so that it can even produce that. And really the root graph could look a bit like that there. Now the restriction that GeoGebra has applied is saying that its range needs to be positive. Okay, now the range is your list of outputs, and we'll cover that in just a second, but it's saying that, well, when you see the GeoGebra part that doesn't have that bit under there and it only produces the positive part, it's saying, well, I'm only going to be able to produce positives. Okay, it's just taking square root of 9 is 3 rather than taking square root of 9 is 3 or negative 3. Now, this isn't a function, and there's a couple of reasons why. You can't plug any value of x in there. Okay, you just can't root a negative when you're talking about real numbers. Okay, there are another set of numbers, but you can't root negative 5. It's just not something that you've learned to deal with, so it just doesn't happen. Also, if we look at it, if I plug in, say, 9, well, there could be any of 2 values coming out. So I can't plug absolutely everything in, and whatever I can plug in, I don't exactly know what I'm going to get out every single time. And so this isn't a function. Okay, this is called a one-to-many mapping. Okay, it's not a function. Now, I've briefly mentioned the word range here. I'm going to talk to you about domain and range now. Now, the domain is the set of inputs that you can apply for a function or for a mapping. Okay. Now, what I always used to think was, with domain, it's got the word in at the end. It's the set of inputs, domain. And range is your set of outputs. So let's take a look at this graph here, x squared. So if we talk about y equals x squared, well, the domain is anything. You can plug anything into that graph, unless you put some restriction on it where you say you can only choose positives or you can only choose integers. The domain's anything you can plug into that, but the range in this case would be only the positive numbers or 0. Okay, greater than or equal to 0. You can't get a negative out when you square something. And so you get some result that will be a restriction on your range. You'll be covering a bit more of that later on in the chapter, but it's worth knowing that those words do come up. Domain is your input, range is your output. Righto. So for each of the following mappings, let's state whether it's one-to-one, many-to-one, one-to-many, and state whether it's a function. Now, you can pause the video in just a second to double check whether you can remember how to do that. But make sure that you're thinking about, when we're thinking about whether something's a function, can you plug absolutely everything in? And based on what you plug in, do you know exactly what you're going to get out? Okay, that's how you decide whether something is or isn't a function. You should make sure that you write that down in your notes as well. So pause the video, give those a go. All right, so question A, part 1, it says, state whether the mapping is a 1-to-1, doesn't look like it, a many-to-one, or a one-to-many. Well, this is actually a 1 value could give us many outputs. Okay, so this is 1-to-many, and so based on 1 value going in and me not knowing exactly what comes out, this is just a mapping. It's not a function. Okay. Next, part B. I should have called that A there. Part B, we've got 1 value going in, exactly 1 value coming out. It's 1-to-1. Now, every value of x could be used. There's no restrictions on it, and so therefore this is a function. Okay, part C. Now this is a little bit tricky. Yes, it's 1-to-1. You plug 1 value in, you get 1 value out. You plug 1 value in, you get 1 value out. But it's not a function. And the reason it's not a function is because it's not defined for absolutely every value of x. Think about it, function. If we plugged in 0 into here, we'd get y equals 1 over 0, which we say is undefined. Okay, we get an asymptote out of that. And if it's undefined, then you're plugging something in and you don't know what you're getting out, and that's the rule about whether something is a function or not. Okay, so it's not a function, it's a mapping, that one. Alright, let's take a look at D. And in this case, we've got many ways to make one value. Okay, we've got many ways, there's many of those making that exact one value there. So that's many to 1, and that is a function. Okay, there's no gaps in it, no asymptotes, none of that sort of stuff that you need to watch out for. Righto, moving on. So, find the range of each of the following functions. So, in this first question here, which is question A, you've got some linear function, which is 3x subtract 2. Now, the domain is a set of integers 1, 2, 3, and 4. Basically, what we're saying is we can only plug 1, 2, 3, and 4 into this. We're not saying we can plug anything else into it. It is integers strictly. So x can equal 1, 2, 3, or 4. So, if x can equal 1, 2, 3, or 4, have a think, what could f of x equal? Well, 1 times 3 is 3, take away 2 is 1. 2 times 3 is 6, take away 2 is 4. 3 times 3 is 9, take away 2 is 7. And 4 times 3, take away 2 is 10. Okay? So we know that what we've got is something that looks a bit like that there. Okay? And so our domain is 1, 2, 3, and 4. And our range, where you've got the x is the set of values 1, 2, 3, or 4, well then f of x, there is a set containing values labelled f of x, which equal 1, 4, 7, or 10. That's your range there. Okay? Is it 1 to 1? Is it many to 1? Well, it's 1 to 1. Okay? You know from each of these outputs exactly which input you went for, and so this is 1, 2, 1. Alright. Next up, let's go for part B. So g of x equals x squared. Now the domain is a set of values with variables labelled x which exist within the real numbers. So that could be decimals, fractions, anything. Okay? It could be anything that you know of. What it can't be, if it's not real, then it could be imaginary, and you'll learn about imaginary numbers if you go on to do the degree, or if you do some background reading, or you're doing further maths or something like that. You'll learn about those. But what we're thinking of is basically your standard number set, which is anything that's a decimal generally, and anything that's a fraction. It could be recurring, it could be a surd, it could be anything. Okay. So what we're saying is that when g of x equals x squared, we've got a domain which is x is going from -5 up to 5. So in this case, rather than dealing with the style that I've done over here, we're going to start understanding that it's better off if we sketch rather than using mapping diagrams. Okay, so a sketch is what we're going to go with. So there's x squared, and what we're saying is that we've got -5 up to 5, and so we can produce values within there. There's no gaps, nothing missing. Okay, let's take a look at what happens if 5 goes in. Well, when 5 goes in, we do 5 squared, which would be 25. Okay, so we have this value up here, which is 25. Alright, now that's fine, our range goes up to 25, that's fine. But what's the lowest output that we could get? Well, the lowest output would be 0, wouldn't it? And we could produce 0, we can produce exactly 0. It's not like a greater than or equal to or anything, a greater than or anything like that. It's a greater than or equal to. And so what we're saying is that the range is the height of this function, basically. It's what sorts of outputs can you get. Well, you could get 0, you could get 1, you could get 2, you could get 3, you could get anything all the way up to 25. You can't get 26, for example, because the input would be too big. It wouldn't fit within the domain. And you definitely can't get out a negative, because you can't square a number and end up with a negative. And so, if the domain is x exists within the real values from -5 up to 5 inclusive, then the range will be a set of values labelled g of x existing within the real numbers, and g of x can go from 0 up to 25. Alright, there's no gaps horizontally or anything like that. That's what our range will look like. Okay, now part C. Now part C you'll recognise from the previous slide. This is a reciprocal graph, and we said that that wasn't a function. Now take a good look at it. We've got h of x equals 1 over x with the domain where x exists within the real numbers, so it can be decimal. But it's from 0 up to 3, but it can't be 0. Now, that restriction on the domain is absolutely key, because if we sketch h of x, we sketch h of x where x is between 0 and 3, then we don't actually include that asymptote. That's for when x is equal to 0. When x is greater than 0, and all the way up to 3, and anywhere further along than that, it is defined. There's a value that you get. So, that restriction on the domain for h of x has meant that this function is, this is a function. It's no longer a mapping. There's a restriction that said, well, yes, there's a value that we couldn't originally use, you know, and so we'll apply this restriction so that this does become a function. Okay, so what we've got is a maximum value. Well, God, it's going to be extremely, extremely, extremely large, isn't it? You know, it's going to be really, 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 really big. Now, my maximum value all the way up here is going to be something. Well, it's got to be close to infinite, I suppose, hasn't it? But you know, just something less than infinity, I suppose. And we've got here, when 3 goes in, we get 1/3. Okay, so the range for h of x is values where h of x exists within the real numbers. We've got h of x, well, that's 1/3. This goes up as high as it could ever go up, so we'll go with is greater than or equal to 1/3, and no further restriction than that. Okay, could be anything provided it's bigger than 1/3. That there is a 1-to-1, and based off of the restriction it becomes a function. By the way, this one was many-to-1. Okay, moving on. Okay, this function, f of x, is defined by this very weird looking set of symbols. So we have f is a function including variables x such that when x is less than 1, we've got 5 subtract 2x as our function. And when x is greater than or equal to 1, we get x squared plus 3 as our function. So a bit weird. Now this is called a piecewise function. It's a piecewise function because it's split into pieces. Okay? Now those pieces do not overlap. They don't overlap. And the reason that they can't overlap is because if they did overlap, then there would be a value of x that you could plug in, and you wouldn't know which of the two functions to use. Now you can see actually the restrictions on the domains here have meant that they don't overlap. Here, strictly we're using stuff that's less than 1. Here we're using 1 or above. So if your value of x that you're choosing is 1, you should know that you're going to be using this one, this part of the piecewise function. Okay, and if your value is less than 1, you should know that you're going to be using the other one. So our job is to sketch f of x. Okay, so first off, we need some rough axes. We know that this is a function that is of a negative gradient, so it's going to be heading that sort of direction there, and that when x is 1, we would get 5 subtract 2x would be 5 subtract 2, which is 3. Okay, so we'd have 1, 3, and what I'm going to do is I'm going to put an empty dot there. We'll see why in just a second. We know also that the y-intercept would be up at 5, and that can help us to feel a little bit more happy about drawing that negative gradient there. Okay. Next up, we've got x squared plus 3. Now x squared plus 3 would go this sort of way, wouldn't it? Okay. And when we say that x is 1, well, 1 squared is 1, plus 3 is 4. So we'd get the value 1 going in and 4 coming out. This would be 1, 4. And any value higher than that, we would get something higher and higher and higher and higher and higher and higher and higher. Okay. Now, this one, this bubble needs to be shaded. And the reason that needs to be shaded is because this is the or equals 2 bubble. Okay. And that's really similar to when you were learning about inequalities on a number line in year 1. You were also learning about it in Key Stage 3 or whatever. Whichever one's got the or equals to is the one that you colour in the bubble with. Okay, so that way it indicates on the graph if you've got x equals 1, you need to use that bubble there. Another thing that I like to do is I like to put arrows on there to say that those are going to carry on forever. So we can produce something extremely, extremely, extremely high. There's no upper limit to our range. Okay, so we've sketched f of x, and now we need to state the range. Well, let's take the very lowest point, and let's see how high it goes. Okay, so the very lowest point you can have is something greater than 3. You can't actually have this bubble, it's an empty bubble. Okay, if we do have 1, we go to this bubble, don't we? Okay, and we head upwards. The range in this case is f of x exists within the real numbers, but also f of x is greater than, and strictly greater than 3. Okay? So next up is asking us to solve f of x equals 19. Now again, this is really key why the graph is quite useful, because 19 would be all the way up here, wouldn't it? And so it is produced on both sides of the piecewise function. Now you could have other functions that don't work that way. You can only produce it on one side, and you'll need to be able to understand, which side it is, whether it's the first part or the second part. So for example, if you had, I don't know, you had something that went like that, and for this one, it might go like that, and you wanted to produce this solution, well, it's only going to happen in that part of the piecewise function, whereas it might look like it could happen if this was carrying on. Okay, it could look like it could happen, but also obviously, there's lots of things there's lots and lots of clues that can help you avoid that. The most key one is your sketch. So f of x equals 19. So f of x can equal 19 based on each of the parts of the piecewise function. So we have f subtract 2x 19, which means that negative 2x is going to equal 14, x equals 7. So when x equals 7, okay, when x equals negative 7, we can see that we can get 19 out. So negative 7, it might be there, and so we can get 19 out. And for our other bit, we've got x squared plus 3 is going to equal 19. And so x squared equals 16, and so x equals plus or minus 4. Now, there's a problem here, because only one of those values can work. The reason why only one of those values can work is pretty obvious. I mean, it only happens once on this curve. Also, x has got to be greater than or equal to 1 in order to make that part of the function work. Okay, so we need to choose x equals 4 as x is greater than or equal to 1. Okay, so your solutions are x equals negative 7 and x equals 4. Okay, so I hope you found this useful. Good luck.